Hello everyone, I am Miss Hu, your physics teacher. In this video, we will be going through the concept of wave diffraction, where we will learn about what is diffraction, the behavior of waves during diffraction, how to draw diffracted waves, and the applications of wave diffraction. Now before we get started on this lesson, just a reminder to subscribe to my YouTube channel for more lessons from your physics teacher, Miss Hu. First of all, let us begin with what diffraction is. So diffraction is the phenomenon when a wave bends around an obstacle and spreads out. What does this mean? Let's look at this in more detail on the next slide. By the way, this animation is just showing us how wave diffraction occurs when it passes through a gap, and we will look at this concept more closely in some upcoming slides. This is just a meme to brighten your day. So let's go into what diffraction is. So what's on this diagram? These black lines are representing the wavefronts of a wave. So you can, for the time being, think of this as wavefronts representing water waves to help you visualize. This red object here is an obstacle that's blocking the waves. That means we're looking at the waves from the top view. So you can think of it as water waves are traveling from left to right, and part of the wave will be blocked by this obstacle that's on the surface of water. Now, because part of the wave is being blocked, obviously only this part of the wave that is not blocked by the obstacle will be able to continue traveling through. So the expectation is that only this part of the wave can continue to travel straight through. But in reality, the wave doesn't get blocked off like that. You'll find that actually this part of the wave will be able to bend around the obstacle and spread out. And the spread is not a random spread. It actually depends on the edge of the obstacle. So the end of the wave fronts here will actually be able to bend around the obstacle, and because they've bent around and been pulled towards the obstacle, they spread out, making the wavefront become longer, like this. So if diffraction didn't happen, we would expect that the entire section behind the obstacle would be completely free of waves. But that's not what happens in reality. We'll find that instead of only this part of the wave continuing straight through, the end of the wave bends around the obstacle and spreads out following the edge of the obstacle, is what diffraction is. Now, the reason as to why waves actually behave like this, meaning that they bend and spread around an obstacle, can be explained using Huygens principle. However, we're not going to go into this principle because this is not covered in SPM or IGCSE. If you'd like to know more about this principle, I will cover that in a separate video. Now, diffraction does occur every day, and this video will show us very clearly how water waves are able to undergo diffraction. You can see these two barriers of rocks are creating obstacles that are blocking the water waves. You can see the water waves are traveling from out here in the middle of the ocean through the gap. As the wave passes through the gap, you can see that the wave spreads out on both sides of the obstacles. So you would expect only this part of the wave to travel through if there's no diffraction, but as the wave passes through, the wave actually goes all the way from barrier to barrier. So let's watch that again. So you can see how from such a short wavefront, the wavefront gets longer and spreads out from barrier to barrier. So the wave diffracts. As it passes through this gap, it bends around both obstacles and spreads out, making the wavefront become longer. So this video shows us very clearly how wave diffraction occurs, and you can see this in real life. Go check it out at the beach. These are photos that also show us wave diffraction. Although the waves are not moving, you can see how in both of these photos, how the waves, when they pass through this gap, spread out behind obstacles on both sides, causing the wavefront to become longer from barrier to barrier. Now we will look at how wave diffraction occurs through gaps, but first of all, let us examine the properties of waves that undergo a change when the waves go through diffraction. So we need to know which of these properties change and do not change. It may not be clear in the video, but it should make a lot of sense. wavelength does not change because the part of the wave that passes through is not blocked by the obstacle. What happens is just that the wavefront gets longer, which means that the wavelength will not change. The frequency will also not change. If you had watched my videos on wave reflection and wave refraction, you would already know this by now. But if you don't know, let me explain this for your benefit. Frequency is kind of like the identity of a wave. Say for example, we have a motor that's creating the water waves. So the frequency of vibration of the motor will be equal to the frequency of the waves that are being generated. And once the waves have been generated, the frequency remains constant throughout the entire wave's lifespan. There is no reason why this frequency would change just because the waves are spreading out when they pass through a gap. So that's why the frequency does not change. The speed also does not change. If you observe the video of the waves moving through, all that happens is that the wave spreads out, but the speed of movement of the wave does not change. So remember that the change of speed is actually refraction, which is caused by other factors. Diffraction is not one of those factors. What does change then? Amplitude does change. And in this case, amplitude decreases when a wave undergoes diffraction. Now, to understand this, remember that amplitude represents the energy of the wave particle. So if the wave starts off from such a short wavefront and then it gets longer, the energy of that short wavefront spreads out when the wavefront becomes longer. So that's why the amplitude of the wave decreases, because the energy has to be spread out along a longer wavefront. That's why the amplitude decreases. Now let's go into understanding the different factors which can affect diffraction. We are going to compare the wavelength of the waves, the gap size, also known as the aperture size, as well as the obstacle size. Now, in order to be able to observe all this, if possible, you should observe these waves in a ripple tank in the lab. So I'm not able to take any videos with a ripple tank at the moment because the ripple tanks in our physics laboratories are not working. So on my slide, I have included a link to an excellent YouTube video which shows us wave diffraction in a ripple tank. I'm not going to be playing this video, but if you'd like to watch this video, do check out the link in my slides, and I will also link this video in the YouTube description below. This is obviously not my video, so I'd like to give credit where credit is due. However, for the purposes of this video lesson, I have included some screenshots so that we can do a quick comparison between those different factors. Starting first with comparing the wavelength. So as you can see in these screenshots, both of these images are showing us gap sizes that are the same. However, the wavelength of the waves are different. The wavelength on the left side is longer compared to the wavelength on the right side. Now look at the spread of the waves that have undergone diffraction. The wave with the longer wavelength has a wider spread compared to the waves that have a shorter wavelength. As you can see, the spread from here to here is longer compared to the spread which is from here to here. So what this tells us is that the wavelength that is longer will have a greater diffraction. To understand this, let me show you step by step logically. So these are simple diagrams where we're going to compare two situations with different wavelengths but the same gap size. So actually, what's a gap? So gap basically is made up of two obstacles that create a small space in between. In your syllabus, sometimes a gap is known as an aperture. Now, because only the middle part of the wave is able to pass through, to help us understand diffraction, let's just draw the middle part of the waves that are passing through the gap. Remember that the wavelength remains the same, because there is no reason why the wavelength would change when the part of the wave can pass through travels through the gap. There are two obstacles, which means that the waves will bend and spread on both sides of the wavefronts. So remember that the spreading of the wave is not random. So to figure out how long the wavefront would be, we'll draw some lines to show the spreading out of the waves as they pass through the gap. So these dotted lines are showing us how the waves will spread. The waves would spread from these ends of the wavefronts to these dotted lines. And remember, they're going to bend. That's why they will curve rather than be a straight line, like so. So what happens is you'll find that the waves will spread out like this. The same thing will happen also for the diagram on the right. But because the wavelength is shorter, you'll find that the spread seems to be a little bit less compared to the wavelength that is longer. Now when we do a side-by-side comparison, you can see that for the wavelength that is longer, the part of the wave that is extended, that means the more curved part, is a lot longer compared to the middle part of the wave, which was straight. Whereas for the wavelength that is shorter, because the wavefronts are so much nearer to each other, the part of the wave that is curved is at a smaller ratio compared to the straight part of the wave. That's why for the wavelength that is longer, the waves appear to be more circular compared to the wavelengths that are shorter. So now, once you understand this, when it comes to your exams, you need to draw clearly how the waves look different. So don't draw it the way I just did. What I've just done is just to show you logically why the wave shapes look like this. Once you know what the wave shape should be, when it comes to your exams, draw the wave shape straight away like this. So that means when diffraction occurs through a gap, when the wavelengths are longer, you need to draw the waves with a wider spread and circular waves. Whereas when the wavelengths are shorter, you draw waves with smaller spread and less curvature, meaning they're plain waves with curved edges. So when we compare waves with different wavelengths, we need to know that the greater the wavelength, the more obvious the diffraction. Now before we move on, let's talk a little bit more about a comparison of these wavelengths. Because the challenge could be, what if they give you a single diagram instead of two diagrams to compare? Do we draw waves that are circular or waves like this? How do we know whether the wavelength is considered to be greater or shorter? We compare the wavelength against the gap size. So in order to know whether to draw circular waves or plain waves with curved edges, we just need to compare the wavelength against the gap size. When the wavelength of the wave is equal to or greater than the gap size, we draw the circular waves. Whereas if the wavelength was less than the gap size, we draw the plain waves with curved edges. So that's how you remember what shape to draw of the waves when they pass through the gap. You compare the wavelength against the gap size. Once you understand this, it's very easy to figure out the rest of the factors. We'll still take a look at them. Let's start off with the gap size first. This is a screenshot from that video comparing the gap sizes for waves with the same wavelength. The screenshot on the left shows us a much smaller gap size, while the screenshot on the right shows us a greater gap size. In both diagrams, the wavelengths of the waves are the same. Although this is quite faint, you can see that the spread of the waves is much greater. In fact, the waves go almost all the way to the barrier on both sides, whereas the waves on the right side have a smaller spread. And if you look at the shapes, you can see how they're similar to earlier, where these are circular waves, while these appear to be plain with curved edges. So how do the gap size explain the shape of the waves? So remember earlier, we learned that we need to compare the wavelength against the size of the gap. So both of these have the same wavelength now, but when you look at the gap size, you can see how this gap size is smaller than the wavelength. This would mean that the spread would be bigger. Let's look at how the waves would travel. So first of all, the part of the wave that can travel straight through is only in the middle, but of course the waves would then bend and spread on both sides of the obstacle. So again, we have the spread lines, and you can see how when the wave spread, the length of the part of the wave that is curved is greater than the part that is straight, creating a curved look. Whereas for the gap size that is much larger, the part of the wave that is curved takes up a smaller length compared to the straight part. So that's why for a smaller gap size, the wave shape seems to change to a circular wave, whereas the gap size that is larger is plain with curved edges. And if we look at the comparison between the gap size and the wavelength, this should make sense. The gap size here is smaller than the wavelength, while this gap size is much greater than the wavelength. So remember that once you know how the shape should be like when you draw the waves for your exam, just draw the shape straight away. So the waves that travel through a smaller gap size will be circular in shape, giving us a wider spread, while the waves that are traveling through a larger gap size would have a smaller spread with less curvature, meaning you draw plane waves with curved edges. If required to compare the gap size against diffraction, we know that the smaller the gap, the more obvious the diffraction. And this should make sense, because smaller gap size means that the gap could potentially be smaller than the wavelength. Now for gap size, it's quite easy to understand, but for some students, but what if it was a single obstacle? For a single obstacle, the video doesn't include this, and in fact, a lot of demonstrations or animations that show diffraction do not cover obstacles. It's easier to observe diffraction with a gap rather than with an obstacle. However, if you're learning about diffraction, you should still learn how waves diffract when they pass around single obstacles like this, so I'll explain this from a theoretical point of view. So if we have a single obstacle like this, what happens now is that instead of only one part of the wave passing through, there'll be two parts of the waves passing around the obstacle, the top and bottom. Let's first compare waves with different wavelengths passing around an obstacle of the same size. So this time we have the top and bottom part of the waves passing around the obstacle. Now, the obstacle is in the middle, meaning that the middle part of the wavefronts would bend around the obstacle and spread out. So the bend around the obstacle is actually going inwards like this. You'll find that the waves will curve towards this spreaded line, and eventually the wavefronts could even combine to form one straight wavefront again. This is also true for what happens for the waves on the right diagram. But you'll find that for waves with greater wavelengths, they seem to join back more quickly compared to waves with shorter wavelengths, even if the area that is blocked over here is of the same size. It is for this reason why we say that the greater the wavelength, the more obvious the diffraction. Remember that diffraction is not about how much of the wave gets cut off. Diffraction is about how much the wave is able to bend and spread. So if the wave can bend around the obstacle and spread out easily and combine easily, that means that the diffraction is more obvious. That's why we say the greater the wavelength, the more obvious the diffraction. Now, let us compare different obstacle sizes. So this time we have two diagrams with identical wavelengths, but we have an obstacle that's larger and an obstacle that's smaller. Similarly, again, only the middle part of the wave gets blocked, so the top and bottom parts of the wave can still pass through. Again, the spread will be inwards because the obstacle is in the middle, and the wave will diffract like this. So the same thing will also happen for a smaller obstacle size, but because the obstacle is so much smaller, the waves will join together to form a single wavefront much more quickly. So you can see that for a smaller obstacle size, the part of the wave that gets blocked is much smaller, and the wave bends and spreads out much more quickly to reconnect and combine into a wavefront again. So remember, diffraction is about bending and spreading out. That's why when we compare these two obstacle sizes, we say the smaller the obstacle, the more obvious the diffraction. Now let's look at some applications of diffraction in real life. So here you can see this is a top view of the sea, and yes, there's wave diffraction. So how is this an application? If let's say we want to be able to reduce the energy of waves that are approaching the beach, what we can do is we can actually build an embankment as such. What we can do is we can actually build a wall as such to cause the wave to diffract as the wave passes around this obstacle towards the beach. You can see how the energy of the waves is so spread out over here. Over here, the waves have quite strong energy, but when it gets around this wall, it diffracts and forms these beautiful circular wavefronts. So this is about spreading out the energy of the waves. Remember that the amplitude of diffracted waves decreases because of the increase in the length of the wavefronts. So building a wall like this forces the wave to diffract and reduces the energy effectively. Now let's look at other situations involving wave diffraction and how to explain them. So a common question you could come across, and in fact this is something you would experience in daily life. How is it that we're able to hear people talking or the source of the sound around a corner even though we can't see them? Now to help us understand this clearly, let's look at this diagram from the top view. Now, in order to be able to see the objects, the light rays need to be able to reach our eyes. The thing is about light is that light waves have very small wavelengths. Now you always hear how people say light travels in a straight line. While that is true, one of the reasons why light doesn't bend around an obstacle is because they have very small wavelengths and do not diffract easily. Remember what we learned earlier. When the wave has greater wavelength, they diffract more easily. So when we compare the light against the obstacle, light has such tiny wavelengths. We're talking about only a few hundred nanometers in wavelength. They do not diffract easily around the obstacle, which means that the light rays will tend to travel straight. Because the light ray does not reach our eyes, we cannot see the source of the sound. Sound, on the other hand, though, have large wavelengths, and therefore they diffract around obstacles easily. So when the sound waves can reach our ears, we can hear the people talking, and this is why we can hear people talking from around the corner even though we can't see them. So if you are required to explain this, you talk about the difference in the wavelengths. Sound waves have much greater wavelengths than light waves and diffract more easily. So this is why we can hear sound from around the corner, but we cannot see them. Now another kind of situation that you might come across is about comparing the different frequencies of sound. So say you have a band that's playing around a corner here, and when it comes to music, there are many different frequencies. So you have the melody, which tends to be of a higher frequency, or you may have bass notes, which are of a much lower frequency. Now, have you ever noticed that you tend to be able to hear only certain frequencies of the sound clearly when you're around a corner, or when it's from a source quite far away? You tend to hear the lower frequency notes, right? The boom, 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 boom. It's quite hard to hear the higher pitch melodies. And this is because, again, the comparison between the wavelengths. So looking again from the top view, so sound waves with lower frequencies, which means that they have longer wavelengths, tend to diffract more easily around a corner. So these kind of notes tend to be the bass notes. The melody, which have higher frequency, tend to be shorter wavelengths, and shorter wavelengths do not diffract easily around the corner, which means that it's more difficult for these kind of notes to be able to reach our ears, as you can see from this diagram. So when we compare them side by side, you'll find that sound waves with longer wavelengths, that means lower frequency, diffract more easily and are able to reach the listener. So this is why we tend to hear the bass notes and not the melody from the same source blocked by obstacles. Here's a little meme to finish up this video. Light travels faster than sound, and this is why some people appear bright until you hear them speak. So here's another comparison between the different applications of wave diffraction. Remote controls. If you have a remote controlled gate at home, or you have seen remote controlled gates being operated, you'll find that the kind of wave they use in these kind of remote controls are different from the remote controls that are used to switch on and off devices like a television. So what's the difference here? In order for this to work, the remote control needs to send waves to the receiver in order to control the gate. So when we're outside trying to open and close the remote controlled gate, obviously there will be obstacles around us. Could be another car, could be a person blocking, could be even the walls that are blocking the receiver of the remote control. So the wave that we need to use in this situation has to be waves of much longer wavelengths. So we tend to use radio waves in order to be able to operate the remote controlled gate. For television, you'll notice that if you're trying to switch on and off or change the controls on the television, you need to point the remote control directly towards the receiver on the television. So these kind of waves tend to be of higher frequency. We usually use infrared waves. As you may or may not know, radio waves have much greater wavelengths compared to infrared. If you're not aware about these kind of waves, please watch my video on electromagnetic waves, where we compare the different kinds of electromagnetic waves and how they're used in daily life. But once you understand the difference between these electromagnetic waves, that means the different wavelengths, it will help you understand better why these different waves are selected for different functions for remote controls. So waves with greater wavelengths, like radio waves and microwaves, are always used for situations like these, where there tend to be a lot of obstacles that could be blocking us. So radio waves or microwaves are used for controlling remote controlled gates, or even to open and close your car. Whereas infrared tends to be used for devices at home like televisions and air conditioners, because for one, higher frequency waves can carry more data, but that is also why you need to point the remote control directly towards the receiver on the device. Here's another application of wave diffraction in daily life, comparing communications. Again, this is related to electromagnetic waves. So let's compare radio waves and microwaves. Now, radio waves have longer wavelengths than microwaves. So say this is the transmitter sending out the data, and this is a house in a remote area. In order for the area to be able to receive the signals sent by this transmitter, obviously the wave needs to be able to reach the receiver. But in this case, we have a huge obstacle blocking, a hill. So in order for the wave to be able to reach the receiver, the wave that is used must have long wavelengths in order to be able to diffract around this large obstacle. So the waves that are used in this situation tend to be radio waves. So these kind of waves are normally used for radio transmission. That means like the radio you listen in your car, where you just twiddle a dial and the receiver in your car can pick it up quite easily. These radio waves are also used for the free national broadcasting. That means the free national channels, where in order to watch them, you just need to put an aerial on your roof and they pick up the signals quite easily. Now, radio waves are good, but microwaves are usually preferred for broadcasting because the higher frequency waves can carry more data, meaning you have clearer video and audio. But a problem with microwaves is that they have greater frequency, meaning shorter wavelengths. Shorter wavelengths, as you can recall, do not diffract easily around an obstacle. So if this transmission tower was to use microwaves for the communication, it would not be able to reach the receiver because there's an obstacle blocking its path, like so. Does that mean it's impossible for microwaves to be used? No. Microwaves can still be used, but microwaves have to use a satellite to relay the information. That means that the transmission tower needs to send the signal first to the satellite, and then the satellite would send the data straight down to the receiver like this. This only works, of course, if there's nothing blocking the signal, and that's why the satellites must be high up in space so that the signal can be sent straight up to the satellite in the sky, and then the satellite can send the data straight down to the satellite dish. So if you have a satellite dish at home, this is why the satellite dish needs to be placed in such a position where there's nothing blocking the receiver on the satellite dish. So when we compare the radio waves and microwaves side by side, you can see that radio waves diffract easily around an obstacle because of their long wavelengths. Microwaves can be used, but we need to use satellites to relay the data. So here are the worded explanations to what I've just said. Radio waves have longer wavelengths, meaning lower frequencies, and can diffract around obstacles easily. Microwaves have shorter wavelengths, meaning higher frequencies, and do not diffract easily. This is why television and radio broadcasting and communications which use radio waves can be easily received by antennas. However, satellite broadcasting and communications which use microwaves have to use satellites to relay the signals. And that's the end of this video lesson. So if you found this video to be educational and helpful, do click like and comment on how this video has helped you. If you would like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Do check out the videos on my channel on other topics which you might find helpful. Subscribe for more free physics lessons from your physics teacher, Miss Ho. Happy studying!